You wake up, you flip a switch, the room turns bright, and there is no sense of delay at all. You look at a star or at the moon, and it just looks present, right now. To your brain, light feels instant. For most of human history, people didn't just notice that feeling, they trusted it. They treated light as something that doesn't travel with a speed, it simply appears. But before we continue, please subscribe to the channel to give your support. Let's continue. Back then, there were no high-speed cameras, no electronics, no precise clocks. You had eyes, torches, the sun, and the night sky. When you see something, it feels synchronized with your action. You move your hand, you see your hand. You don't see any lag. So the default conclusion was simple and wrong. Light has no travel time. Even major thinkers went along with that. Aristotle, for example, talked a lot about motion and how things move through a medium, but he didn't treat light as a signal that you could time. For daily life, it didn't matter. Across the distances people cared about, meters or a few tens of meters, any travel time for light was far below what human senses can detect. So the idea that light might have a measurable speed didn't feel urgent. But not everyone was comfortable with that. Some ancient thinkers pushed a more strict line of reasoning. Empedocles basically said, if something goes from one place to another, it takes time, even if that time is small. Light starts at a source and ends at your eyes, so it should have a non-zero travel time. That means it has a finite speed. On the other side, people like Aristotle said, even if there is any delay, it's too small to detect. So as far as real life is concerned, you can treat it as infinite. So you had a strange situation. People were arguing about whether the speed of light was finite or infinite, but nobody had a number, nobody had data, and nobody had an experiment that could even see a delay. It was a debate about a quantity that might not even exist in any practical sense. It was philosophy, not physics. The real problem is just how extreme the numbers are. In vacuum, light travels about 300,000 kilometers every second, roughly 186,000 miles every second. That is the standard figure you hear, and it is not a round guess, it is a hard measured constant. Now compare that to the scales in your daily life. Take a room that is 5 meters long, about 16 feet. The time light needs to cross that room is on the order of a few tens of nanoseconds. A nanosecond is a billionth of a second. So we're talking about something like 0.000000017 seconds for that trip. Now compare that to you. A typical human reaction time from seeing something to pressing a button is about 0.2 seconds. That's millions of times slower than the light crossing the room. So if your experiment is basically, I will turn on a lamp and see if there is any delay in when I notice it, you're out of luck. The delay is there, but it is 10 million times smaller than the jitter in your own nervous system. This is why early attempts to think about light speed went nowhere. Any direct human-scale measurement is doomed. Your eyes and brain are just too slow. You would need either enormous distances, way beyond anything in a city or a battlefield, or timing tools that can slice time into tiny fractions of a second. For a very long time, nobody had either. And that meant the question, does light have a speed, looked almost academic. You could live your whole life, build cities, fight wars, do astronomy at a basic level, and never see a single piece of evidence that light takes time to go anywhere. The sun rises, you see it. A torch is lit, you see it. Lightning flashes, you see it almost at the same time you hear the thunder, unless it's far away. In that environment, saying light might have a finite speed sounds like nitpicking. But here's where the stakes quietly get high. You're not just talking about a number, you're talking about how cause and effect work in the universe. If light were truly infinite in speed, then events across the universe could, in principle, share the same now. A star exploding in a distant galaxy would be visible at the exact instant it exploded, with no delay. The idea of simultaneous everywhere would be simple. There would be no built-in limit on how fast information could move. Distance would make things dimmer, but not later. If light has a finite speed, even one as huge as 300,000 kilometers per second, everything changes. Then, every time you look at something far away, you're seeing it as it was, not as it is. The sun you see is about 8 minutes old. A nearby planet could be dozens of minutes out of date. A star could be years out of date. A distant galaxy could be millions or billions of years out of date. The night sky becomes a record of the past, not a live feed. More importantly, if there is a maximum speed at which light and other signals can travel, then there is a maximum speed for information, for influence, for any cause to affect something far away. That maximum speed sets a hard limit on how fast the universe can update. It defines which events can possibly affect which other events, and how quickly. That's not a side detail, that is the backbone of causality. So when people later start to actually measure the speed of light, they're doing much more than filling in a value in a table. They're testing whether there is a universal speed limit at all, and if there is, how big it is. They're testing whether now is really shared across space, or whether now is local, and the rest of the universe is always delayed. For a long time, the gap between the philosophical debate and a real measurement stayed huge. No tools, no distances, no clocks that could resolve tiny delays. But eventually, someone tries anyway. He picks the only timing instrument he has, human reaction time, and he asks a simple question. Can I notice any lag when light travels a few kilometers and back? That person is Galileo. He uses 2 lanterns and a couple of hills, and his result looks like a failure until you realize how much it actually tells you about how fast light has to be. How do you measure something that outruns your own reflexes by a factor of tens of thousands? In the early 1600s, Galileo Galilei decides to try anyway. No lasers, no electronics, no telescopes that can time tiny delays, just 2 people, 2 lanterns, and a couple of hills separated by a few kilometers. It sounds simple, it feels like it should work, and it is almost guaranteed to fail. But that failure is exactly why it matters. Here's the setup in plain terms. Take 2 experimenters, you and your partner, you walk out to one hilltop, they walk out to another, roughly 1 to 2 kilometers away from you, so around half a mile to a little over a mile. Each of you hold a lantern with a cover over it. The rule is clear and strict. You uncover your lantern, and the instant your partner sees your light, they uncover theirs. You watch for their lantern to flare, and you try to time how long it takes from your action to their response. On paper, it feels like a clean test. If light speed is truly infinite, then the only delay between your lantern and theirs should be your partner's reaction time, the time it takes their brain to see the light and their hand to move the cover. If light has a finite speed, you might see an extra tiny delay, which would tell you that the signal itself is taking time to cross the gap between the hills. Galileo is basically lining up light's travel time against human reaction time and see if there's any extra sliver left over. Now compare the 2 timescales. Take a distance of about 2 kilometers, a bit over a mile. At 300,000 kilometers per second, light covers that gap in about 7 millionth of a second, 7 microseconds. Your reaction time, even if you're very alert, is about 2/10 of a second, which is 200,000 microseconds. Light wins by a factor of around 30,000. So in Galileo's test, the interesting part, the travel time of the light, is a tiny bump buried deep inside the much larger noise of human reflexes. When Galileo actually runs the experiment, the outcome is exactly what those numbers predict. He doesn't see any extra delay he can trust. For short distances, and even for a few kilometers, the time from uncovering his lantern to seeing the response looks, as far as his senses and crude timing can tell, basically the same as a simple reaction time. In his notes, the conclusion is cautious but clear. If light has a finite speed, it must be extremely large, far beyond what this method can measure. If it's infinite, this is also what you'd see. The experiment can't tell the difference. On the surface, that sounds like a failure. You ask a yes or no question, is the speed of light finite? And the experiment gives you, I can't tell. There's no clear lag, no obvious stutter, nothing dramatic. You flick the cover, you see the other lantern, it feels immediate. The result matches your everyday intuition. Light seems instantaneous. But if you look closer, this nothing result is actually very informative. First, it means that light is at least much faster than anything you could hope to measure over naked senses over kilometer distances. If the light had taken, say, 1/10 of a second to cross between you and your partner, you would have seen that as a clear extra delay on top of their reflex. You didn't. That already tells you light speed is not small. It's not like sound in air, a few hundred meters per second, where you clearly hear a delay between lightning and thunder. It's in a completely different league. You can even turn this into a rough lower bound, using only the crude timing Galileo had. If all he can say is, there's no delay larger than a couple of tenths of a second, and the distance is a few kilometers, then the speed has to be at least a few kilometers divided by a couple of tenths of a second. That gives a minimum value of around 10 kilometers per second, roughly 6 miles per second. Today you know that is tiny compared to the real number, but for the early 17th century, that's already a useful statement. Light is not slow, it is not comparable to sound, it is way beyond arrows, cannonballs, or anything else people could launch. So what did Galileo actually achieve here? He did 3 important things at once, even though he didn't get a clean number for the speed of light. First, he took the problem out of pure philosophy and moved it into the lab. Before this, people argued in words. One side said, everything that moves takes time, so light must take time. The other side said, we don't notice any delay, so it might as well be infinite. Galileo's lantern test is the first serious try to turn that into an experimental question. You don't just speculate, you build a setup, you define rules, you test, you record what you see. Second, he exposed the core difficulty in a very concrete way. If your signal is extremely fast and your timing tool is extremely slow, you will learn almost nothing about the signal. Human reaction time is a blunt instrument. Over short distances, it completely swamps the delay you're trying to detect. So Galileo's result quietly tells future scientists, if you want to measure light, you cannot rely on your own senses. You need either much larger distances or timing systems that are way sharper than human reflex. Third, he showed that a null result still narrows the possibilities. Not seeing a delay doesn't mean there is no delay, it means the delay is smaller than the resolution of your setup. That gives you a range. You can say, light speed is bigger than this minimum value. That minimum is crude, but it is still a real scientific statement, and it is much better than we know nothing. It's easy, centuries later, to laugh at that lower bound. 10 kilometers per second is nothing compared to the true speed of 300,000 kilometers per second. But remember the tools. No digital timers, no high-speed film, no precise mechanical clocks with millisecond markings. Galileo is trying to measure something more extreme than any speed he has ever encountered using a stopwatch made of flesh and nerves. In that context, it's less like a mistake and more like a first probe, a first poke at a wall that turns out to be much harder than he expected. There's also a subtle lesson in experimental design hiding here. If your signal is too fast for your timing device, you don't just give up. You change the game. You either increase the distance the signal has to travel, so even a very high speed still produces a measurable delay, or you find an indirect way to turn that tiny delay into something else you can see more easily, like an angle, a phase shift, or a pattern. Galileo's lanterns are the direct, brute force approach. They fail. Future experiments will be all about clever geometry, astronomical baselines, and mechanical tricks that effectively slow the measurement down without slowing light itself. So Galileo ends up in an awkward middle position. He knows light is fast, he knows it is too fast for his method, but he can't pin it down. He hasn't killed the idea of infinite speed, and he hasn't proved finiteness with numbers. What he has really done is expose the scale of the challenge. Human scale setups are not enough. If you want to beat light, you have to involve something bigger than hills and lanterns. That realization points in a very specific direction. If a few kilometers are too short, what about hundreds of millions of kilometers? If human reaction time is useless, what about natural repeating events that act like a clock far away in space? In other words, if two people on neighboring hills can't catch the delay in light, what happens when you time the eclipses of a moon circling Jupiter and watch them drift by minutes as Earth moves around the sun? How do you measure the speed of light when your stopwatch has to be the size of the solar system? By the 1670s, you finally have something good enough to try it not on hills with lanterns, but across hundreds of millions of kilometers, using Jupiter and its moons as moving parts in a giant clock. Here's the key upgrade. Compared to Galileo, you now have decent telescopes. You know Jupiter is a planet, not a wandering star, and you know it has moons orbiting around it. One of those moons, Io, is especially useful. It orbits Jupiter in about 1.77 days, so just under 2 days. Every time Io swings behind Jupiter and disappears into Jupiter's shadow, from your point of view on Earth, that moment is like a tick. It's a repeating event, regular, predictable, and you can write down the predicted times on a schedule. Roemer looks at this and thinks very differently from the philosophers before him. He doesn't ask, does light have a speed? He asks, if light has a speed, can these eclipses act as a timing signal to reveal it? If light were truly infinite in speed, then the timing of those eclipses as seen from Earth should only depend on Io's orbit around Jupiter. The ticks of that cosmic clock should arrive right on schedule no matter where Earth is in its own orbit around the Sun. The geometry might change the angle you look from, but not the time the light takes to get here. Because in the infinite speed picture, that time is always zero. So astronomers start doing the boring but critical work. They watch Io over and over, month after month, year after year. They predict when each eclipse should happen based on orbital mechanics, and they compare it to when they actually see it happen through their telescopes. At first, the data just looks messy. The eclipses are sometimes on time, sometimes a bit early, sometimes a bit late. It would be easy to blame bad instruments, bad predictions, or just sloppy observing. But Roemer sees a pattern that won't go away. When Earth is on the side of its orbit where it's moving toward Jupiter, the eclipses of Io seem to arrive earlier than predicted. When Earth is moving away from Jupiter, the eclipses happen later than predicted. And as Earth moves from the nearest side of its orbit to the farthest side of its orbit, the delay slowly builds up, reaching a maximum of about 22 minutes. Then, as Earth swings back around and starts coming closer again, the delay shrinks. That's the crucial point. It's not random noise, it's systematic. Over roughly half a year, as Earth travels to the far side of its orbit, the light from Jupiter has farther to go, and the observed eclipses of Io appear later and later. Over the next half year, as Earth comes back around, the distance shrinks and the observed eclipses move back toward on time. This regular drift, up to about 22 minutes of lag and then back down again, is the clue that something more than bad prediction is going on. So what could cause this? The orbit of Io around Jupiter doesn't care where Earth is. Jupiter and Io are doing their thing, with Io circling Jupiter in its 1.77-day rhythm. If the mechanical model of Io's orbit is right, the only thing that can make the eclipses seem late or early from Earth is the travel time of the light carrying the news of those eclipses to you. Roemer makes a bold move. He assumes the orbital model is basically correct, and he treats the changing eclipse times as a pure signal of light's travel time. When Earth is closer to Jupiter, the light has less distance to cross, so you see the eclipses earlier. When Earth is farther away, the light has more distance to cross, so you see the eclipses later. The maximum swing in distance from closest to farthest is roughly the diameter of Earth's orbit around the Sun, about 300 million kilometers, which is around 186 million miles. Now, put that together with the timing. At the farthest point, the eclipses are delayed by up to roughly 22 minutes compared to when they should be seen if light were instantaneous. 22 minutes is about 1,320 seconds. So Roemer says, in plain language, light takes about 1,320 seconds to cross an extra 300 million kilometers. If you take that distance and divide it by that time, you get a speed of roughly 230,000 kilometers per second, about 140,000 miles per second. Today, you know the true value in vacuum is about 300,000 kilometers per second, so Roemer's number is low. But keep in mind what he's doing. He's not timing a beam in a lab. He's not using electronics. He's using the entire orbit of Earth as the baseline, the orbit of Io as a clock, and slow, human-made tables of predicted eclipse times, all in the 1600s. Just getting the right order of magnitude, hundreds of thousands of kilometers per second, is a huge achievement. For the first time, the speed of light is not maybe infinite, maybe not. It's a finite number, with units, built from real data. This is where the old picture really breaks. Up to this point, you could kind of defend the idea that light might be instantaneous, or so fast that you didn't need to treat it as having a travel time. After Roemer, that position collapses. If the speed of light were infinite, then Earth's changing distance from Jupiter would not matter for the timing of Io's eclipses. But it does. The data shows it clearly. There is a delay. It grows and shrinks in step with Earth's orbit, and it fits perfectly with the idea that light has to cross a larger or smaller gap. That means, in very simple terms, when you look at Jupiter, you are never seeing Jupiter now. You are seeing Jupiter as it was minutes ago. When Jupiter is on the far side of the Sun from you, that delay is larger. When it is closer, that delay is smaller. The planet is always running ahead of the light you get from it. And if that's true for Jupiter, it's true for everything else as well. So the sky changes character. It stops being a flat map of things as they are and becomes a time-layered map of things as they were. Planets, stars, galaxies, all of them are shifted backward in time by an amount that depends on their distance. Roemer's 22 minutes for Jupiter is on the small side, but once you admit that light takes time to travel, there's no reason to stop there. Double the distance, double the delay. Go to the nearest stars, and now you're talking years. Go to distant galaxies, and you're talking millions or billions of years. The speed of light and its finiteness turns a universe into a kind of built-in time machine. And notice something else. Roemer's method is completely different from Galileo's. Galileo tried to directly feel a delay with his own reactions over a distance of a few kilometers. Roemer lets the solar system do the work over hundreds of millions of kilometers, and he reads the delay from a drifting schedule. He's not trying to watch light creep along. He's using orbital mechanics and timing errors as a way to magnify the effect until it becomes obvious. This is a shift in style that will keep repeating. When you can't measure a speed directly because it's too fast, you let some large-scale, slow process convert that speed into a shift in time or angle that you can measure instead. Roemer uses timing shifts in Io's eclipses. Others after him will use tiny angles in the apparent positions of stars. Different techniques, same constant. By the late 1600s, thanks to this work, instantaneous light is no longer a serious option. Light has a speed. That speed is enormous, but it's finite. And once you know that, you can ask a harder question. If light has a finite speed and Earth is moving through space, does that motion leave any trace in the angles where we see stars, the same way rain seems to tilt when you walk through it? If timing delays prove that light is slow enough to measure, can angular shifts prove that its speed is tied to Earth's orbital motion and give an even cleaner value? How do you prove Earth is moving using stars that seem frozen in place? In the early 1700s, you still don't have a direct, everyday proof that Earth goes around the sun. Copernicus and Kepler have the math, but people want a clean observation, a shift in star positions caused by Earth's orbit, something you can point to and say, there, that's the motion. James Bradley goes after exactly that, and he ends up measuring something different, something that quietly nails down both Earth's motion and the speed of light at the same time. Here's what Bradley is trying to see. If Earth orbits the Sun, then over 6 months it moves from one side of its orbit to the opposite side, a change of about 300 million kilometers, around 186 million miles. Nearby stars should appear to shift slightly against the background of more distant stars as your viewpoint moves. That tiny wobble in position is called stellar parallax. It's a straightforward piece of geometry, but the angle is incredibly small, way below what casual observing can see. Bradley builds extremely careful instruments to measure star positions night after night, all year long. He picks bright stars and tracks their positions very precisely. He expects to see a simple pattern. As Earth moves around the Sun, each nearby star should trace a little loop or line on the sky with a size set by its distance. Closer stars should shift more, farther stars should shift less. That would be the clear, visual mark of Earth's orbital motion. But that's not what he sees. Instead, he finds something unexpected. The stars do shift over the year, but not in the way parallax predicts. The shifts are almost the same size for many different stars, and they all seem to lean in a direction related to Earth's orbital motion, not in a way that encodes each star's distance. The pattern is wrong for parallax, but it's not random. It repeats yearly, it has a clear direction, and the maximum angle is about 20.5 arc seconds, which is roughly 1/10,000th of a right angle. Tiny but real. So now Bradley has a new problem. He set out to prove Earth moves by seeing parallax, and instead he's found a different, consistent annual effect that also seems tied to Earth's motion. If it's not parallax, what is it? This is where the walking in the rain idea comes in, and we'll keep it very simple. Think of raindrops falling straight down relative to the ground. If you stand still, the rain hits your head straight down. If you start walking forward, the rain hits you from a slight forward angle because you are moving sideways while the drops are moving down. You feel like the rain is slanted, even though to the ground's frame, it's still falling straight down. The faster you walk compared to the fall speed of the rain, the more you have to tilt your umbrella forward. Now replace raindrops with starlight. In the rest frame of the star, light comes straight towards you, but from the point of view of an observer on Earth, Earth is moving sideways in its orbit at about 30 kilometers per second, around 67,000 miles per hour. The light is racing in at about 300,000 kilometers per second. Because you're moving while the light is arriving, you have to tilt your telescope slightly into the direction of Earth's motion to catch the light beam. That tilt is what Bradley is seeing. It's called the aberration of starlight. The key point is that this aberration angle depends on the ratio of Earth's orbital speed to the speed of light. When that ratio is small, the angle is small. In simple terms, the angle in radians is roughly equal to Earth's orbital speed divided by light speed. Earth's speed is known fairly well by orbital mechanics by this time, about 30 kilometers per second. Bradley has measured the angle, about 20.5 arcseconds, which converts to a bit less than 1/10,000th of a radian. So now you have everything you need. If the angle is roughly Earth's speed divided by that tiny angle, dividing by such a tiny number multiplies the speed by 10,000. You get roughly 300,000 kilometers per second, about 186,000 miles per second. That's right on top of the modern value, and Bradley got it without timing pulses, without watching light go and come back. He got it from a tiny tilt in the direction he has to point his telescope throughout the year. There's another layer to the story. Aberration doesn't just give you light speed, it also proves Earth's motion in a direct, brutal way. Parallax depends on the distance to each star, so you could, in principle, hide the effect by saying maybe the stars are unimaginably far away. Aberration doesn't let you escape like that. The effect depends only on Earth's speed and light speed. If there were no orbital motion, there would be no annual aberration pattern. The fact that the whole sky shows this systematic tilt tied to Earth's known orbital direction locks in the idea that Earth really is moving around the sun. So now step back and look at what you have by the mid-1700s. Roemer used timing delays in Io's eclipses to argue that light takes about 1,300 seconds to cross the extra 300 million kilometers of Earth's orbit, giving a speed of a couple of 100,000 kilometers per second. Bradley used a tiny angular tilt of star positions combined with Earth's 30 kilometers per second orbital speed to get roughly 300,000 kilometers per second. Two completely different methods, one based on timing, one based on angle, both using the solar system as a measuring device, both pointing to the same range, hundreds of thousands of kilometers every second. This agreement is not just a nice detail. It crushes the idea that these results are accidents or artifacts. If Roemer had gotten one order of magnitude and Braden had gotten something wildly different, you might say our models are wrong or something else is going on. Instead, they line up. They both say light is fast, but not infinite. It has a definite speed, and that speed is a stable property of nature, not a number that depends on where you look or how you measure. At this point, the speed of light is no longer a guess or a philosophical toy. It has become a constant you can lean on. You know it's huge, you know it's finite, and you know it connects Earth's orbital motion, the timing of distant moons, and the apparent positions of stars into one coherent picture. Space, time, and motion are now linked by a single number. But there's still an obvious gap. So far, every serious measurement of light speed depends on astronomy, Jupiter's moons, Earth's orbit, star positions. What if all of those models are subtly off? What if you want a measurement that lives entirely on Earth, over distances you control, using apparatus you can tweak and rebuild in a lab? Can you bring this cosmic constant down to ground level and measure it with a machine you can touch without relying on planets and stars at all? That's the next step, and it's a big one. It means building experiments where light travels kilometers, not astronomical units, and timing its journey without using human reflexes. It means spinning metal wheels so fast that, for once, light speed isn't the only extreme thing in the setup. Why should you trust the timing of a distant moon or the tiny tilt of a star if you've never seen light measured right here on Earth with hardware you can almost touch? By the mid-1800s, that's the pressure physicists feel. Astronomy has given a clear message: light is fast and finite, but it still feels like nature's doing the experiment for you. Hippolyte Fizeau decides that isn't enough. In 1849, he drags the problem down from the sky and forces it to play out over French countryside, using a light source, a distant mirror, and a brutally fast-spinning wheel. Here's the core idea. You send a beam of light out over a known distance on Earth on the order of several kilometers, and you send it through a wheel with evenly spaced teeth and gaps cut into its edge. The light passes through one of the gaps, travels about 8.6 kilometers, roughly 5.3 miles, hits a mirror on the far side, and comes back along the same path. On the way back, it has to pass through the wheel again. Whether it makes it or not depends on how far the wheel has rotated while the light was in flight. If the wheel is turning slowly, the returning light still finds an open gap, and you see it back at your end. If the wheel is turning faster, the timing changes. You can reach a speed where, by the time the light completes the round trip, the gap you originally used has rotated into a tooth. Now, the tooth is sitting where the opening used to be, and the light slams into metal instead of passing through. At that rotation rate, the returning beam disappears. It's blocked completely. That's the key observation. You find the rotation speed where the light flips from visible to gone. To make this work, the wheel is not some crude gear. It has a lot of teeth, hundreds of them, something like 720 teeth and 720 gaps. That means each tooth and each gap is a tiny slice of the full circle. As the wheel spins, a given point on the rim cycles through gap, tooth, very quickly. The time it takes for the rim to move from a gap position to the neighboring tooth position is tied directly to how fast the wheel spins and how many teeth it has. If the wheel makes hundreds of full turns per second, those tiny gap-to-tooth transitions are happening in microseconds or less, exactly the kind of timescale that light's flight time over tens of kilometers lives in. So, Fizeau does something very simple but very powerful. He starts at a low rotation rate where the returning light is clearly visible through the wheel. Then he turns up the speed, watching what happens to the brightness of the returning beam. At a certain rotation rate, the light vanishes, because every returning ray that left through a gap comes back just in time to meet a tooth. If he cranks the wheel even faster, eventually another gap lines up at the right moment and the light reappears. But that second step isn't even strictly necessary to get a first good estimate. The first off point already pins down the round-trip tidal time of the light in terms of the wheel's rotation. Now, translate that into timing, in plain language. You know how many teeth and gaps are on the wheel. You can measure how many full turns per second the wheel is making when the light is just blocked. From those two facts, you can figure out how long it takes for the rim to move from a position of a gap to the next tooth position. That time is a tiny slice of a second, and by design, it matches the time light needs to go from the wheel to the mirror and back, about 17,266 meters, roughly 17.3 kilometers, which is around 10.7 miles. Once you have that, the rest is the basic definition of speed: distance divided by time. The round-trip distance is about 17.3 kilometers. The round-trip time is that tiny slice of a second you just extracted from the rotation speed and tooth count. When Fizeau puts his actual measurements together, he gets a value for light speed of around 313,000 kilometers per second, which is about 194,000 miles per second. That's a bit higher than the modern value of roughly 299,800 kilometers per second, but it's impressively close for a first purely terrestrial precision shot. Think about what that really means. No Jupiter, no Io, no star positions, no orbital geometry. Just a light source, a tooth wheel, a distant mirror, and careful measurement of distances and rotation rates. You can walk the baseline, you can adjust the apparatus, you can repeat the procedure hundreds of times. The speed of light stops feeling like an astronomical curiosity and starts feeling like an ordinary, if extreme, lab quantity, something you can measure on a cloudy afternoon. The level of engineering here is also important. This is still the 1840s. There are no digital counters, no photodiodes, no oscilloscopes. Fizeau has to build a wheel that can spin at hundreds of revolutions per second without flying apart. He has to count those rotations, and he has to align a light beam across nearly 9 kilometers to hit a mirror and come back through the same small apparatus. Any sloppiness in distance, angle, or speed shows up directly in the result. The fact that he lands within a few percent of the modern value tells you the setup was extremely well controlled. This experiment does more than just add another data point. It changes who can play the game. Now, any well-equipped lab, in principle, can measure the speed of light without waiting for planetary alignments or carefully tracking star positions for a year. You can treat light speed as something to check, to refine, to tie into other measurements instead of treating it like a weird number you only get from astronomy. It also shifts attitudes. Once you've measured C on Earth and you see that it matches the astronomical values in the same ballpark, your confidence goes way up. You start to suspect that this speed is not just a property of starlight or of sunlight, but a universal property of light itself, whether it comes from the sun, a flame, or a lamp in your lab. That's a big step toward the idea that C is a constant of nature, the same everywhere, the same for any kind of light in vacuum. But Fizeau's method, powerful as it is still relatively blunt. The wheel is mechanical, the gaps and teeth are macroscopic, and the distances are long. The accuracy is good, but not yet at the level where you can probe tiny differences, like how much slower light travels in water compared to air, or where small systematic errors could hide. The next logical move is to keep the main idea. Measure how far light goes in a tiny slice of time, but replace the wheel with something smoother and more controllable, something that can turn continuous motion into continuous angular shifts on a screen. That next move is exactly what Leon Foucault makes. He swaps teeth for mirrors, turns timing into a shift in the spot of light you see, and shows not only that you can sharpen the value of C on Earth, but also that light really does slow down in dense media, backing the wave picture of light and knocking down the old particle model. How do you turn a time so small you can't possibly measure it into a distance you can literally see moving across a screen? In 1850, Leon Foucault answers that by swapping Fizeau's clunky spinning wheel for something cleaner and more controllable, a rotating mirror. Same basic goal, measure how long light takes to go out and back, but now you turn that tiny time delay into a tiny angular shift, and then into a visible spot moving on a wall. Here's the setup in simple terms. You have a bright light source. You send a narrow beam toward a small mirror that is spinning at a steady, high speed. That rotating mirror reflects the beam toward a fixed mirror some distance away. The light hits the fixed mirror, bounces back to the rotating mirror, and then gets sent off toward a screen where you can see a spot of light. The crucial detail is that while the light is traveling out to the fixed mirror and back, the rotating mirror does not sit still. It turns by a very small angle. If the mirror were not rotating, the outgoing and incoming directions would be the same, and the spot on the screen would sit in one fixed place. But when the mirror is spinning, by the time the light comes back, the mirror has turned a little, so the returning beam is reflected at a slightly different angle. That small change in angle makes the spot on the screen shift sideways by a small but measurable distance. Faster rotation, bigger shift. Longer light travel time, bigger shift. In other words, the amount the spot moves is directly tied to how long the light was in flight. The trick is that angles and distances are easier to measure precisely than microsecond intervals, especially in the 1850s. You can put the screen several meters away, or even tens of meters away, which amplifies the angular change into a millimeter scale movement on the wall. A tiny rotation of the mirror might only be a few millionths of a turn, but if the beam travels, say, 20 meters or about 65 feet, that tiny angle opens into a spot shift you can see with a measuring microscope. Now, think about how Foucault pulls the speed of light out of this. He knows the distance between the rotating mirror and the fixed mirror. Call that something like a few tens of meters in a lab setup, or in some versions, a few kilometers, a mile or two. The light does a round trip, so it covers that distance twice. He also knows how fast the mirror is spinning, in turns per second. From that, he can work out how far the mirror turns during the light's round trip. That angle, doubled by the reflection geometry, tells him how much the outgoing and incoming beams are separated on the screen. So, in words, here's the chain. Measured rotation rate gives you how far the mirror turns in 1 second. Multiply that by the unknown travel time of the light, and you get the tiny angle the mirror turns during that flight. That tiny angle, combined with the known distance to the screen, gives the sideways shift of the spot. You measure that spot shift in millimeters. Now you have a link between mirror rotation speed, spot shift, and travel time. You solve for the travel time, then use distance equals speed times time to get the speed. Same basic physics as Fizeau, but with angles and a rotating mirror instead of gaps and teeth. Foucault's method has some big advantages. You don't need an 8-kilometer baseline. You can do a lot even inside a building or with a shorter outdoor path. You don't rely on blocking and unblocking a beam completely. You look at a continuous shift in position, which lets you use many data points and average out noise. And because everything is smoother and more adjustable, you can push for higher precision and check for systematic errors more easily. But Foucault doesn't stop at just measuring light in air. He wants to know what happens when light travels through different materials. That goes straight into one of the hottest debates of the time, the nature of light itself. Is light a stream of particles like Newton's corpuscles, or is it a wave in some medium? Here's why this matters. The particle model, as Newton set it up, actually predicts that light should travel faster in denser media like water or glass than in air. The wave model predicts the opposite, that light should slow down in denser media, with the slowdown factor linked to the refractive index, the same number that shows up when you talk about bending of light in lenses and prisms. So, if you can directly measure light speed in air versus in water, you're not just getting more digits for C, you're choosing a side in a fundamental fight about what light is. So Foucault modifies the setup. He leaves everything else the same, but he puts a section of the light path inside a tube filled with water. Now the light spends part of its journey inside water instead of air. If light slows down in water, then for the same geometric distance, the travel time will be longer. Longer travel time means the rotating mirror turns a tiny bit more while the light is in flight, which means a slightly larger angular change and therefore a larger shift of the spot on the screen. He runs the experiment both ways, first with air, then with water, and he sees exactly that, a difference in spot position that corresponds to a slower speed in water. When he crunches the numbers, the speed of light in water comes out to about 225 million meters per second, which is around 140 million miles per second, while in air it stays close to 300 million meters per second, around 186,000 miles per second. The ratio of those speeds matches very well with the known refractive index of water, about 1.33. That is exactly what the wave theory says should happen, and the opposite of what Newton's naive particle picture would suggest. So, in one stroke, Foucault is doing two jobs. He's sharpening the terrestrial value of C, bringing it very close to the modern number, and he's showing that light really does slow down in denser media in a way that matches wave theory. His final result for C in air ends up around 298,000 kilometers per second, about 185,000 miles per second, only a little below the modern vacuum value. Considering that he's working with metal bearings and glass, that accuracy is impressive. Look at the progression you've seen so far. Galileo, no delay at human scales. Roemer, delays of tens of minutes across Earth's orbit. Bradley, a tiny angular tilt in star positions that encodes the ratio of Earth's speed to light speed. Fizeau, a spinning toothed wheel and an 8.6 kilometer baseline, giving a solid first terrestrial number. Foucault, a rotating mirror turning time into shift on a screen, nailing down C to within a few percent, and proving light really does slow down in water in the way wave theory demands. Each step cuts out excuses. Each new method uses different systematics, different possible errors, and yet they all converge on the same basic figure, about 300,000 kilometers every second. By the time Foucault is done, the speed of light is no longer just very big. It's a specific constant that seems to show up consistently whether you're timing moons, tracking stars, or bouncing beams between mirrors. That consistency is exactly what you need before you can start suspecting that this number is built into the equations of deeper physics, not just an accident of optics. And that's where the story is about to escalate, because in the next step, you don't measure C from light at all. You measure purely electrical and magnetic effects in the lab. You plug those values into a formula from a new unified theory, and out pops a speed that matches Fizeau and Foucault almost exactly. Suddenly, light isn't just whatever comes out of lamps and stars. It's an electromagnetic wave, and C is no longer just the speed of light, it's the natural speed of the electromagnetic field itself. How do you know you've really understood something in physics, not just measured it? One sign is when you can predict the number from a totally different direction before you even do the experiment. By the 1860s, people have decent values for the speed of light from astronomy and from terrestrial setups like Fizeau and Foucault. But now, James Clerk Maxwell writes down a theory of electricity and magnetism that quietly spits out the same number using no optics at all. That's the moment the speed of light stops being just how fast light goes and becomes a built-in property of the universe. Up to this point, electricity and magnetism are like two awkward relatives. You know charged objects can attract and repel. You know currents in wires can create magnetic fields. You know moving magnets can induce currents. There are a bunch of separate laws, each describing one type of behavior. They work, but they feel disconnected. Maxwell takes all those separate laws, translates them into math in a consistent way, and stitches them together into one unified framework. When he does that, something new drops out. The equations don't just describe static fields and steady currents, they also allow changing fields. A changing electric field produces a magnetic field. A changing magnetic field produces an electric field. Put those together, and the mathematics says, very bluntly, these two can chase each other through space as a self-sustaining wave. You disturb the electric field in one place, that creates a magnetic disturbance, that creates more electric disturbance further out, and so on, spreading outward. No charges moving along with it, just the fields themselves. Here is the important part. The math doesn't leave the speed of that wave as a free parameter. It gives you a specific value for that speed, written in terms of two constants that describe how electric and magnetic fields behave in empty space. One constant, the permittivity of free space, tells you how strongly electric fields respond in vacuum. The other, the permeability of free space, tells you how strongly magnetic fields respond. Combine them in the way the equations tell you to, take the square root, take the inverse, and you get a single speed. Those constants are not exotic. Experimentalists have already measured them in completely boring lab setups, long before Maxwell. You charge up capacitors and see how much electric field you get for a given charge and geometry. That gives you the permittivity. You run currents in coils and measure the forces between them. That gives you the permeability. None of that has anything to do with beams of light or telescopes. It's all meters, kilograms, seconds, charges, and forces in a lab. Now, Maxwell and others plug the actual measured values into the expression the theory gives for the wave speed. They're not thinking, this must be the speed of light. They're just following the math. Out comes a value of about 300 million meters per second, so 300,000 kilometers per second, about 186,000 miles per second. In other words, the speed of these hypothetical electromagnetic waves in vacuum is essentially the speed of light that Roemer, Bradley, Fizeau, and Foucault have been hammering on from completely different directions. That's the jaw-drop moment. Two sets of experiments, totally different physics on the surface, converge on the same speed. On one side, optical setups and astronomy. On the other side, coils, capacitors, and magnets with no light explicitly involved. The only reasonable conclusion is that they're talking about the same thing. Light is an electromagnetic wave. When you switch on a flashlight, you're not sending out mysterious light particles in the old Newtonian sense. You're launching ripples in the electromagnetic field that spread through space at that natural speed set by the constants of vacuum. This changes how you talk about C. Before Maxwell, C is the speed of light in vacuum, a property of something specific that comes out of lamps and stars. After Maxwell, c is the speed that electromagnetic disturbances must have in vacuum according to the structure of the field equations. Light just turns out to be one particular range of those waves, the visible range your eyes are sensitive to. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all of them are the same type of thing, electromagnetic waves, all traveling at that same basic speed in vacuum. So the number that used to sound like a detail now looks like a constant baked into the laws of physics. You don't get to choose it. Once you pick units and once you measure those electric and magnetic constants, the wave speed is forced. It's not light happened to come out at this speed. It's if you live in a universe with these field laws and these constants, any free electromagnetic wave has to move at that speed. That's a much deeper statement. And that leads straight into a nasty conceptual problem. Waves usually need a medium. Sound needs air or some other material. Water waves need water. If electromagnetic waves can move through empty space at this fixed speed, what is waving? 19th century physicists answer, there must be a special medium filling all of space, the luminiferous ether. Light waves are vibrations of that ether. Once you say that, you've committed to something testable. If there is an ether and light speed is defined relative to it, then if Earth moves through the ether, you should see small differences in the measured speed of light depending on whether you're measuring along or across Earth's motion, similar to how the speed of sound and air depends on whether you measure with or against the wind. Maxwell's theory itself doesn't demand an ether, but many people think that must be there because they're still using the old intuition that every wave needs a medium. Now, look at the tension you've created. On one side, you have a beautifully unified theory of electricity and magnetism, with a natural wave speed that matches the measured speed of light. On the other side, you have the expectation that this speed is defined relative to some special rest frame, the ether. If that rest frame exists, you should be able to detect Earth's motion through it. But the more precise your light speed experiments become, the less room there is for any directional difference. So the question becomes brutal and simple. This speed that Maxwell's equations predict and that experiments keep finding, is it the speed relative to some hidden medium, or is it a speed that every inertial observer will measure the same way no matter how they're moving? If it's tied to a medium, you should see an ether wind. If it's truly universal, then our basic assumptions about space and time, inherited from Newton, are in serious trouble. That's the next phase. You try to catch the ether in the act using even more precise interferometers and long baselines. You expect to see light speed wobble slightly as Earth moves in its orbit and rotates on its axis, and instead you get nothing. Over and over, the speed of light comes out the same in every direction you check. The theory that united electricity and magnetism has now cornered you into questioning the very structure of space and time itself. How far can you push a measurement before it starts to push back on your entire picture of reality? By the late 1800s, the speed of light isn't just big, it's already known to a few significant figures. But Albert Michelson isn't satisfied. He wants more digits, less doubt. He wants to turn c into one of the sharpest numbers in all of science. And in doing that, he ends up tearing a hole in the idea of an ether and cornering physics into changing space and time themselves. Michelson's first move is straightforward. Take Foucault's rotating mirror idea and scale it up, hard. Short lab paths are fine for a first estimate, but if you want more precision, you want light to travel much farther so that any timing error becomes a tiny fraction of the total flight time. So he builds setups with baselines of tens of kilometers, in some cases arranging for light to bounce between distant sites, even mountaintops, so that the beam effectively travels dozens of kilometers out and back. The principle stays the same. You send a beam to a rotating mirror, it reflects to a distant fixed mirror, comes back, and the rotating mirror's motion while the light is in flight shifts the outgoing and returning directions just enough that the spot on a detector moves. You know the path length in meters, you know how fast the mirror is rotating, you measure how far the spot moves, and from that you infer how long the light took to do the round trip. Distance divided by time gives you c. The difficulty is in doing this precisely, not just once, but over and over. Long baselines mean you need very accurate distance measurements, down to fractions of a millimeter over many kilometers. Rotating mirrors mean you need incredibly stable speeds, controlled and monitored carefully, not drifting all over the place. Air means you have to track temperature and pressure because they slightly change the index of refraction and therefore the effective speed. Michelson spends years chasing down every correction he can think of. Why bother? Because every reduction in uncertainty tightens the noose on any theory that wants to wiggle out. If you know C only to a few percent, you can blame mismatches on error bars. If you know it to a tiny fraction of a percent, then the theories either match that value or they're wrong. Michelson is turning C into a weapon against sloppy thinking. His final results land around 299,796 kilometers per second, about 186,284 miles per second. Modern measurements give 299,792.458 kilometers per second. The difference is less than a few kilometers per second out of almost 300,000. That's an error of under 0.002%. With 19th century tech, that's the level where C becomes one of the best known constants in all of physics. Now comes the next question. If C is that well measured, and if Maxwell equations say electromagnetic waves travel at c in vacuum, relative to some medium or frame, can you detect Earth's motion through that medium? If there's an ether and light has speed c relative to it, then moving through the ether should be like moving through a wind. You should measure slightly different effective light speeds depending on whether you're going upwind or downwind with respect to the ether. This is where Michelson teams up with Edward Morley. Together, they design what's now famous as the Michelson-Morley interferometer. The idea is simple in logic, even if the implementation is delicate. Split a beam of light into two paths at right angles to each other. One path goes, say, along the ether wind, the other path goes across the ether wind. Then you recombine the beams and look at the interference pattern, the pattern of bright and dark stripes created by the overlapping waves. If the speed of light is slightly different along the two paths because of Earth's motion through the ether, then the travel times will differ slightly. That time difference shows up as a shift in the interference pattern. Rotate the whole apparatus, and as the angle changes relative to the supposed ether wind, the pattern should slide back and forth. Measure that slide, and you've measured the difference in light speed along different directions. From that, you can work out how fast Earth is moving through the ether. They build the device with absurd care. The whole interferometer is mounted on a floating stone slab so it can be rotated smoothly. Path lengths are matched to within tiny tolerances. They check for vibration, for temperature gradients, for anything that could move the fringes. They know what kind of shift they should see if Earth is moving through the ether at about 30 kilometers per second, its orbital speed. And then they run the experiment. They turn the platform, they watch the fringes, they repeat at different times of day, different times of year to catch different orientations of Earth's motion. The expectation is a clear periodic shift as the apparatus rotates relative to the ether wind. Instead, the shift they see is either zero or far too small to match the predicted effect, buried in noise. Within the sensitivity of their device, the speed of light is the same along both arms, no matter the orientation. No clear ether wind, no preference direction. This is a shock. It's not just one anomalous reading, it's a systematic failure to detect any directional dependence of C at the expected level. The simplest interpretation is brutal. Light speed is not changing with Earth's motion the way ether models say it should. Either the ether is being dragged in some special way, or its interaction with matter is bizarrely tuned, or the whole idea of an ether as a preferred rest frame is wrong. Because C is now known so precisely, you can't hide this behind measurement uncertainty. You can't say, maybe our distances are off by a few kilometers, or maybe our timing gear is sloppy. The same Michelson who nailed C to 5 significant figures is now not seeing any directional difference where the ether picture says there must be one. The more carefully he measures, the worse the ether idea looks. The community doesn't give up the ether immediately. People propose all kinds of fixes. Maybe objects moving through the ether contract in length along the direction of motion by just the right amount. Maybe clocks slow down in a particular way. Maybe the ether is dragged along with Earth. But every patch has to be tuned incredibly carefully to not only match Michelson-Morley, but also the success of Maxwell's equations and all the other light speed measurements. So now look at the situation around 1900. You have 1. A well-measured, almost absurdly precise value of C from multiple methods. 2. Maxwell's theory which predicts that electromagnetic waves travel at C in vacuum. 3. No detectable ether wind, even with an instrument designed specifically to see it. You are stuck. If you assume ordinary Newtonian space and time, plus an ether, you're fighting your own data. If you accept the experiments at face value, you're stuck with the idea that every inertial observer measures C, regardless of motion. That directly contradicts the naive way we add velocities in everyday life, where speeds just stack. This is the pressure cooker Einstein walks into in 1905. He doesn't ignore Michelson and Morley. He takes their null results seriously. He doesn't throw away Maxwell. He takes the constant C in the field equations as non-negotiable. His move is to throw out something else instead. The idea that time and space are absolute and the same for everyone. He keeps C fixed and lets simultaneity, lengths, and time intervals become relative. So when you think about special relativity, don't picture it appearing out of nowhere. It's what happens when precise, repeated, and increasingly brutal measurements of the speed of light leave physics no way out. The number C is too solid to bend, so the structure of space and time has to bend around it. How do you respond when nature tells you one speed never changes no matter how you move? By 1905, that's exactly the corner physics is stuck in. Every careful experiment says the speed of light in vacuum is the same, even when the source moves, even when you move, even when Earth orbits the sun. Maxwell's equations bake that speed into the laws of electromagnetism. Michelson and Morley failed to find any ether wind. The data is screaming, this speed is special. Most people are still asking, why does C look the same? Einstein flips it. He asks, what if this is just how the universe works, and then refuses to back down from the consequences. His move is clean and ruthless. He promotes the weird experimental fact to a basic rule. If you're in any non-accelerating frame of reference, you measure the same speed of light in vacuum, regardless of your motion or the light source's motion. He doesn't treat that as a glitch. He treats it as a starting point. He keeps another old rule too, that the laws of physics look the same in all such frames. Then he asks, very directly, what does that force space and time to do? The answer is special relativity, and it is not gentle. If C is fixed for everyone, then your measurements of time and distance cannot be fixed for everyone. Clocks in relative motion cannot agree on how much time passes between two events. Rulers in relative motion cannot agree on how long an object is. Simultaneous for you cannot mean simultaneous for someone flying past you at a large fraction of C. Take a concrete example. You have a spacecraft cruising at 80% of light speed relative to Earth. In metric units, that's about 240,000 kilometers per second. In imperial, around 150,000 miles per second. From the ship's point of view, everything on board feels normal. Your heart rate, your experiments, your coffee break, all tick along as usual. But when someone on Earth calculates how your onboard clocks are running using Einstein's rules, they find those clocks are slow compared to theirs. Time on the ship is dilated when viewed from Earth. Distances along the direction of motion are contracted. Your 1 meter stick on the ship, when measured from Earth's frame, comes out shorter. None of this is optional. It's not a side effect. It's the only way to keep the speed of light the same for both of you. Light has to outrun your ship at the same speed in every frame. The only way to make the numbers match is to let time and length flex. They become frame dependent while C stays rigid. Once you accept that, C stops being just a speed and becomes the universe's hard limit. No signal, no information, no object with non-zero rest mass can reach or exceed that value. You can push as close as you like, but you never cross it. At low speeds, like a few kilometers per second, where rockets live today, the relativistic corrections are tiny, so Newton's approximations still work. But as you push towards serious fractions of C, the cost of acceleration climbs brutally. Talk in fractions because that's how high-speed physics really works. 10% of light speed is about 30,000 kilometers per second, roughly 19,000 miles per second. The relativistic effects are there, but modest. 90% of light speed is about 270,000 kilometers per second, around 168,000 miles per second. And now time dilation and length contraction are huge. Each extra 10% closer to C costs far more energy than the last 10%. By the time you get to 99% of C, pushing to 99.9% is not just harder, it's vastly harder. The math says that to actually hit C with a massive object, you'd need infinite energy. That's the universe telling you this barrier is non-negotiable. So the number that started as how fast does light go turns into the thing that sets the rules for energy and momentum at high speeds. It governs how particles behave in accelerators, how cosmic rays hit the atmosphere, how jets from black holes stay collimated. It's baked into every formula that deals with velocities close to light speed. You don't get to step outside it. Then Einstein pushes further and finds something that sounds simple and turns out to be devastatingly powerful. Mass and energy are two ways of describing the same stuff, linked by the square of the speed of light. In words, the energy locked into a mass at rest equals that mass multiplied by c times c. Take c as about 300 million meters per second. Square that and you get about 9 times 10 to the power 16 in units of meter squared per second squared. That's a ridiculously large factor. Now attach 1 kilogram of mass to that factor. 1 kilogram is about 2.2 pounds, a bag of sugar, a bottle of water. Multiply that by 9 times 10 to the power 16 and you get around 90 quadrillion joules of energy. That's the kind of output a large city would use over many years. All of that is sitting silently in a single kilogram of ordinary matter just because c is so large and because the link between mass and energy uses c squared. The gigantic value of c that everyone fought to measure over centuries is exactly what makes nuclear energy and the power of stars possible. When you hear about nuclear reactors, nuclear weapons, or the fusion reactions that power the sun, you're seeing mass being traded for energy at that conversion rate. You only ever convert a small fraction of the mass because the factor is so huge. The whole nuclear age hangs on the same C that Roemer pulled from Jupiter's moons and Michelson nailed with rotating mirrors. But the real shock for your everyday intuition is what this constant does to the idea of now. In pre-relativity thinking, there is one global present. Two events either happen at the same time or they don't, full stop. Once C is finite and universal, that picture breaks. Imagine you're on Earth and you say two flashes of light on opposite sides of a long train track happen at the same time because you see their light arrive together. Someone on a fast train moving along that track will not agree with you. Because light speed is fixed and signals take time, the moving observer will conclude that one flash happened before the other. Both of you are using valid procedures to define simultaneous. Both procedures assume the same C, and yet you disagree on the ordering of the events. That's not a trick of perception, it's built into the structure of space-time. Mathematically, what's really going on is that you're living in a four-dimensional space-time, with 3 dimensions of space and 1 of time tied together. The speed of light acts as the conversion rate between space units and time units. Roughly speaking, 1 second of time corresponds to about 300,000 kilometers of space along the axes of this space-time structure. Transformations between observers moving at constant relative speed mix space and time coordinates, but they preserve the space-time interval, which includes c as the conversion factor. That's why c stays the same in every inertial frame, while distances and durations shift. So the act of measuring c, over and over with more and more precision, did much more than fill in a constant on a chart. It forced you to abandon absolute time, forced you to accept that simultaneity is relative, forced you to see mass as stored energy, and to accept that there is a hard speed limit for all information. It took something that started as an optical nuisance and turned it into the backbone of modern physics. But even after Einstein, you're not done. If C is this fundamental, if it shapes space-time and energy at every scale, You don't just accept it and walk away. You keep trying to measure it in new ways at new precisions, with new technology, looking for any crack at all. So the question becomes, now that you have lasers, electronics, and atomic clocks, how do you time light's flight directly in microseconds and nanoseconds? And can you still squeeze more truth out of a speed you think you already know? If you walked into a modern lab today and said, I want to measure the speed of light myself, right now, how would you actually do it? You don't have mountains, you don't have spinning mirrors on distant peaks, but you do have lasers and electronics that can slice time into billions and even trillions of a second. The basic idea hasn't changed. You still time how long light takes to go from A to B and back. The difference is, now your stopwatch is an oscilloscope, and your light source is a laser pulse that lasts a few nanoseconds or less. Here's the straightforward version. You set up a pulse laser, something that spits out very short bursts of light rather than a continuous beam. You point it at a reflector a few hundred meters away. Round trip, you're talking maybe 1,000 meters of path, around 3,280 feet. You put a photodiode at the sender end, a device that converts light into an electrical signal, and connect that to a high-speed oscilloscope or a time-to-digital converter. You trigger the laser and start the clock electronically at the same moment. Then you watch for the returning pulse and stop the clock when the photodiode voltage spikes. Light needs about 3.3 microseconds to travel 1,000 meters round trip. A microsecond is a millionth of a second. Modern electronics don't just resolve microseconds, they comfortably resolve nanoseconds, billionths of a second, and in some setups even picoseconds, trillionths of a second. So if your total flight time is on the order of a few microseconds and you can measure that to a few nanoseconds, you're already down at parts per thousand accuracy. Push to picosecond resolution and you're probing parts per million. The game then is simple but picky. You measure the total travel time very accurately, you measure the distance very accurately, and you divide. 1,000 meters in 3.3 microseconds gives you roughly 300 million meters per second. You repeat with different distances, different reflectors, different cables, checking that your electronics themselves aren't adding weird delays. It feels almost casual compared to Fizeau and Michelson, but under the hood, it's the same race between light and your timing hardware. The difference is, your stopwatch is finally caught up enough that light can't just shrug it off. Then comes a very useful twist. You don't actually need open air. You can use optical fiber as a controlled, coiled-up racetrack for light. Say you have a precisely manufactured fiber that's exactly 1 kilometer long, about 0.62 miles. Light doesn't move at full vacuum speed inside glass. Because of the refractive index, roughly 1.5 for typical fiber, the speed drops to about 200 million meters per second, around 124,000 miles per second. That means a pulse needs about 5 microseconds to traverse that 1 kilometer of fiber. Now plug in modern timing tools. Time-to-digital converters and high-end oscilloscopes can resolve delays down to tens of picoseconds or even better. A picosecond is 1/trillionth of a second. In that time, light in vacuum moves about 0.3 of a millimeter, around 1/100th of an inch. So if you can measure changes in flight time of a few picoseconds, you're resolving path length differences on the order of fractions of a millimeter over kilometers of fiber. That lets you calibrate the effective speed of light in that medium to absurd precision and monitor tiny changes in the fiber, like thermal expansion or stress. Engineers use variants of this all the time. They send short pulses down long fibers to map delays, find faults, and verify that a given link really is the length they think it is. Physicists use similar tricks to sync events in big experiments, making sure that signals arriving from different detectors are time-stamped correctly even when they've traveled through different cable runs. Underneath it all is the same operation. Send a pulse, detect it, measure the time difference, and turn that into a speed using a known distance. But you don't even have to watch pulses move anymore if you don't want to. There's another way. Instead of measuring travel time and distance, you measure the light's wavelength and its frequency, then multiply. In plain terms, the speed of a wave equals how far one wave peak is from the next, multiplied by how many peaks pass a point each second. That's it. So if you know the wavelength in meters and the frequency in cycles per second, their product gives you the speed. Frequency metrology is where this gets crazy precise. Modern lasers can be locked to atomic transitions, and atomic clocks can keep frequency stable to 1 part in 10 to the 15 or better. That means if the frequency is, say, a few hundred trillion cycles per second, you can nail that number down to within a tiny fraction of a cycle per trillion. Wavelength can be measured by comparing them to carefully stabilized optical cavities and interferometers. Those measurements get tied back to the meter, which itself is defined using C, so you have to be careful about circular definitions. But historically, people did this when the meter was still defined in other ways. When you put these pieces together and you measure frequency and wavelength independently, you can compute speed without ever watching a pulse fly across a lab. You just multiply a length scale by a time scale. That approach got so good that eventually the measurement problem flipped around. Instead of, we know the meter, let's measure C, metrologists said, we trust C so much we're going to define it to have an exact value, and use it to define the meter. That's the 1983 move, but the groundwork comes from all this high-precision frequency and wavelength work. So you might ask, if you've defined C exactly, why even bother doing new measurements? Isn't the discussion over? The answer is no, and the reason is simple. Every different method stresses a different part of the system. Time of flight measurements test your distance calibration and your timing electronics. Fiber-based methods test how well you understand refractive indices and dispersion. Frequency wavelength methods test your atomic clocks, your optical cavities, and your control of environmental effects. Interferometry tests how well you can compare phases of waves over long paths. When all these methods, with all their different possible error sources, converge on the same constant, you gain confidence not just in the number, but in the entire structure of physics that assumes that number is universal. If any one method started to drift away at high precision in a consistent, reproducible way, that would be a red flag. Maybe C depends slightly on energy, or direction, or gravitational potential. That would crack open new physics. So far, it hasn't. Within experimental uncertainty, every careful modern test says the same thing. In vacuum, light speed is fixed. You change the medium, you slow light. You compress or cool atoms, you can mess with group velocities and pole shapes. But when you correct for all that and ask about the underlying constant in empty space, you keep landing back on the same value. That raises the next question, and it's one that hits both technology and deep physics at the same time. If C in vacuum is so solid that we use it to define the meter, how exactly do we handle the messy reality that almost all light you care about is not in vacuum at all? It is always passing through some medium. So the next critical step is to measure how matter changes light speed and keep that carefully separated from the underlying constant you've thought so hard to pin down. The basic tool for that is the refractive index. In plain language, the refractive index of a material tells you how much slower light travels in that material. It is defined as the ratio between the speed of light in vacuum and the speed of light in the material. If it is 1.33, like for water, that means light travels 1.33 times slower in water than it does in vacuum. If it is around 1.5, like for standard glass, light is slowed by that factor in glass. Put numbers on it. In vacuum, light moves at about 300 million meters per second, around 186,000 miles per second. That's your C. In water, with a refractive index around 1.33, the speed drops to about 225 million meters per second, roughly 140 million miles per second. In ordinary glass, with a refractive index near 1.5, the speed is about 200 million meters per second, around 124,000 miles per second. Those are still huge speeds, but the differences matter because lenses, fibers, and even the delay in your internet connection all depend on them. So how do you actually measure that slowdown in a lab without chasing individual photons? One classic way uses prisms and lenses and a simple piece of geometry called Snell's law. You send a narrow laser beam into a transparent prism at a known angle, and you measure the angle at which it comes out or bends inside the material. You do this with a device called a goniometer, which lets you read angles to fractions of a degree. The amount of bending depends on the refractive index. Higher index, stronger bending. From those measured angles, Snell's law gives you the refractive index directly. You know the entry angle in air, you know the bend angle inside the prism, and the relationship between them has that index built in. Once you have the index, and you already know c in vacuum from other experiments, you immediately know the speed of light in that material. You are using centimeter-scale hardware and degree-scale angles to infer speeds of hundreds of thousands of kilometers per second, all anchored on the vacuum c that's now defined with insane precision. There is another, very practical area where this matters: fiber optics. Most of the global internet backbone is light and glass. When data travels between continents, it rides on pulses of light in fibers laid along the ocean floor. Those fibers are often thousands of kilometers long, and the fact that light travels slower in glass than in vacuum shows up directly as latency, the time delay you feel when you do a video call or send a packet from one side of the planet to the other. Take an undersea cable about 6,000 kilometers long, roughly 3,700 miles. In vacuum, a light signal would cross that in about 20 milliseconds, or 1/50th of a second. In glass, where the speed is about 200 million meters per second because of the refractive index, the one-way travel time is closer to 30 milliseconds, or about 1/30th of a second. Round trip, you're already at about 60 milliseconds before you add in any routing or processing delays. That is a delay you can feel. Your speech and the other person's speech start to step on each other when you talk. Engineers measure and model these speeds by sending test pulses, measuring round-trip times, and matching them to cable lengths and refractive indices. The same physics Foucault used with water in the 1850s now controls the responsiveness of your online games and stock trades. In telecom and in metrology, people don't just accept the speed in fiber is about 2/3 of c and stop there. They characterize the exact effective index of each fiber type as a function of wavelength, temperature, and manufacturing variations. Small changes in refractive index over wavelength, called dispersion, stretch and reshape light pulses as they travel. That affects how far you can send data before it blurs, and how fast you can push bits through the system without them overlapping and corrupting. Measuring all of that still depends on knowing c in vacuum, and then carefully tracking how the medium modifies the wave's speed and shape. Then there are the truly extreme slow light experiments that sound like they break everything you've been told. Physicists can take specially prepared materials, like ultra-cold atomic gases near absolute zero, shine in carefully tuned laser beams, and arrange things so that a light pulse's group velocity drops to a few meters per second, basically walking speed. In some setups, they can even effectively halt the pulse, store its information in the medium, and then release it later. On the surface, that sounds like a disaster for relativity. If you can crush light speed down to a crawl in one system, can you also push it above c in another? Doesn't this mess with the idea of a universal speed limit? The answer is no, and this is where your definitions matter. In a medium, you have several different velocities you can talk about. The phase velocity is how fast individual wave peaks move. The group velocity is how the envelope of a pulse moves. The front velocity is the speed at which a truly new disturbance, like the first turn-on of a signal, propagates. In exotic materials, you can make the group velocity very small, or even make it behave in weird ways, but the actual information, the new signal front, never outruns c. The local group velocity dropping to a few meters per second does not mean causality has slowed to that pace. It means the medium is heavily reshaping the pulse, buffering and releasing energy in a controlled way. Some experiments even report apparent superluminal group velocities, where a pulse peak seems to exit a medium before it should if it were traveling at c. Again, no actual information or energy crosses the medium faster than c. The shape of the pulse gets distorted so that the peak shifts forward, but if you try to encode a new message at the leading edge, that leading edge still respects the c limit. The fine print is subtle, but the conclusion is sharp. No matter what you do to a material, you do not get a real signal to leap ahead of light and vacuum. That's why the original vacuum measurements of c remain the anchor. You treat c as the baseline speed in empty space, then every medium is characterized by how it slows or reshapes light relative to that. Refractive indices, dispersion curves, slow light tricks, they all live on top of that foundation. If any experiment in any medium ever produced a clear, repeatable way to send information faster than c in vacuum, you would be staring at a serious breach in relativity. So far, every time someone thinks they see that, a closer look shows that the pulse definition they're using is not the one that matters for causality. So now you're in an interesting position. You know c in vacuum exactly. You know how to measure how matter slows light to different speeds. You can calculate latencies across oceans, design lenses for cameras and telescopes, and even engineer materials where light crawls at human walking speed. And through it all, the vacuum c stands unchanged as the true upper limit. Once you trust that constant, you can flip the usual question. Instead of how fast does light go between here and there, you can say, given this time delay and this constant speed, how far away must that source be? In other words, you can start using light travel time as a ruler for the universe itself. How do you measure the distance to something you can never visit, never touch, and might already be dead by the time you see it? Once you know the speed of light, you stop thinking only in kilometers or miles. You start thinking in time, because every photon that reaches you has a built-in delay stamped into it, and with c in your pocket, that delay is a ruler. Start small. Take 1 second. In that 1 second, light in vacuum travels about 300,000 kilometers, around 186,000 miles. That's 1 light second. Stretch it to 1 minute, 60 seconds, now you've got about 18 million kilometers, roughly 11 million miles. When you say the Earth is about 8.3 light minutes from the Sun, you're saying sunlight takes a bit over 8 minutes to cross that gap of roughly 150 million kilometers, about 93 million miles. If the Sun vanished, you would not find out for those 8 minutes. That's the delay built into the distance. Astronomers also use astronomical units, AU, where 1 AU is roughly that Earth-Sun distance. Jupiter might be, say, 5 AU away from the Sun at some point in its orbit. Multiply the 8-minute light time by 5 and you get 40 to 45 light minutes, depending on the exact geometry when Earth and Jupiter are on different sides of the Sun. So 5 AU isn't just a fancy length, it's a time delay you can feel. When you see something happen near Jupiter, you're seeing something that finished more than half an hour ago. Now scale up hard. A year is about 31.5 million seconds. Light traveling at 300,000 kilometers per second for that long covers roughly 9.46 trillion kilometers, around 5.88 trillion miles. That distance has a name: 1 light year. It's not a time in this context, it's a distance defined by a time. You pick 1 year, multiply by c, and that product is now a standard unit. The nearest star system beyond the Sun, Alpha Centauri, is about 4.37 light years away. That means the photons hitting your eyes from there left around 4 and a bit years ago. If you're 18 now, you're literally looking at light that started its trip when you were 14. The Milky Way, our galaxy, is on the order of 100,000 light years across. That means if a signal left one edge and tried to cross to the other at light speed, it would need 100,000 years to get there. You can't think about those scales sanely in kilometers. The numbers are too big. But in light years, you can at least track the delay. And this only works cleanly because you know c numerically. Without a hard value for c, light year would just be a poetic phrase. With c nailed down, a light year is a defined length. You can put it in equations. You can build maps with it. You can compare it to the size of galaxy clusters or the radius of the observable universe. Then there's the parsec, the unit everyone makes fun of in sci-fi, but astronomers love because it comes straight out of geometry. The word comes from parallax second. Think back to Bradley and the hunt for parallax. Earth orbits the Sun, and over 6 months it shifts position by about 2 AU. If a star is relatively nearby, its apparent position against the background shifts by a tiny angle when Earth moves. That angle is the parallax. Define a specific case. If the parallax angle is 1 arcsecond, which is 1/3000th of a degree, the distance to the star is 1 parsec. Do the math once, and you find that 1 parsec corresponds to about 3.26 light years, or roughly 10 trillion kilometers. So when an astronomer says this star is 10 parsecs away, that's about 32 light years. Multiply by c, and you know the light has been in flight for 32 years. This links several earlier ideas into one chain. You use Earth's orbit as a baseline. You measure a tiny angle on the sky, the parallax, with a telescope. That angle and that baseline give you a distance in parsecs. Then you use c to convert that distance into a light travel time. Angles plus orbits plus c equals distance plus age of the light. It's the same logic as Roemer and Bradley, just packaged as a clean distance unit. Modern astronomy builds an entire distance ladder this way. For nearby stars, you use parallax and parsecs. For more distant ones where parallax is too small, you use standard candles like certain kinds of variable stars or supernovae, calibrated using the closer objects. All of those distances, in the end, are converted into light years or megaparsecs, and all of those conversions depend on c being a fixed, known value. Now, stare at the night sky with that in mind. Every object you see has a built-in time delay, and because you know c, you can label that delay. A galaxy 1 billion light years away is not just far, we're seeing it as it was 1 billion years ago. That's long before humans existed, before the continents were in their current positions. You're looking at a fossil record encoded in photons that have been in flight longer than mammals have been around. When a distant star explodes as a supernova, the burst of light doesn't care what's happening on Earth. It leaves when the star dies, then travels for millions or billions of years through mostly empty space. Eventually, a tiny fraction of those photons hit detectors on Earth, either your eyes or telescopes. The exact arrival time gives you not only the time since the explosion in the star's frame, but also, when combined with distance measurements, information about how the universe has expanded while that light was moving. Because c is finite and you know its value, the sky stops being a snapshot and becomes a time-stamped archive. You can say, this quasar is 12 billion light years away, so we're seeing it as it was when the universe was less than a fifth of its current age. You can line objects up by their light travel times and reconstruct a history. Early galaxies, peak star formation, the buildup of heavy elements, the growth of galaxy clusters. And this isn't just abstract cosmology. The same logic runs in your planet-scale systems. Signals from spacecraft in the outer solar system carry a light time delay of hours. Commands you send to a probe near Saturn take over an hour to arrive, and the reply takes another hour coming back. When mission controllers plan maneuvers, they have to factor in that delay. They never see the probe now, they see it as it was. The units they work in, light seconds, light minutes, aren't cute names. They're operational numbers that decide whether a burn happens at the right moment or misses entirely. So once c is fixed, time and distance are no longer separate in astronomy. You don't just ask, how far away is that galaxy? You ask, how long has its light been traveling? And those are the same question with different units. The meter sticks and kilometer odometers you use on Earth are just local tools. At cosmic scales, your real ruler is the clock, and c is the conversion rate from ticks to meters. But that raises another hard question. If c is this central, if time as distance is the way you read the universe, how much of your everyday technology is secretly running on this same constant? When you get directions on your phone, when you make a video call, when scientists bounce lasers off the moon, how much is riding on the assumption that c is exactly what all these measurements say it is? If that number were off by even a tiny fraction, your maps, your calls, your trading systems, your traffic radar, a chunk of modern life would start to drift. Take GPS, the thing that tells your phone where you are on Earth. GPS satellites orbit at about 20,000 kilometers up, roughly 12,400 miles. Each one carries very accurate atomic clocks and constantly broadcasts timestamps down to the ground as radio signals. Those signals move at essentially the speed of light in vacuum. Your phone listens to several satellites at once, reads the timestamp in each signal, and compares it to your own internal clock. From the difference between the satellite's send time and your receive time, your phone computes how far away that satellite is, just by distance equals speed times time. If the signal has been flying for a tiny fraction of a second, multiply that by 300,000 kilometers per second and you get the range. With at least 4 satellites, your phone can solve for your 3-dimensional position and your clock correction all at once. Here's the catch. A 10 nanosecond timing error, that's 10 billionths of a second, turns into about 3 meters of position error, roughly 10 feet, because light travels about 3 meters in 10 nanoseconds. If your clock is off by 100 nanoseconds, now you're 30 meters off, about 100 feet. That's the difference between navigate to this shop entrance and I'm in the wrong building. The entire system works only because C is known and built into the software, and because the satellite clocks are synchronized and corrected for both special and general relativity. The same constant that shows up in Einstein's equations is literally what lets your phone say, "You are here," within a few meters. Now look at the internet backbone, especially long-haul fiber. Inside a fiber, light doesn't travel at full C. It moves at about 200 million meters per second, around 124,000 miles per second, because of the refractive index of the glass. That slowdown is consistent and predictable, which is exactly what engineers rely on. Take a transcontinental fiber link across 5,000 kilometers, roughly 3,100 miles. Even in the ideal case, no routers, no queuing, no overhead, just physics. The one-way travel time for a signal is distance divided by speed. So 5,000 kilometers divided by 200 million meters per second, which gives about 25 milliseconds. One way. Round trip, you're at roughly 50 milliseconds. That's just the light, nothing else. Network engineers call this the latency budget. They design routing algorithms, data center placements, even stock trading strategies around these hard limits. You can optimize your code, compress your packets, remove hops, but you cannot make light cross that glass faster than the physics allows. When gamers complain about ping, when traders care about microseconds between New York and Chicago, they are dealing directly with the same C that Roemer got from Jupiter's moons, just slowed by glass and multiplied by distance. Then there's laser ranging to the moon, which is almost comically clean as a physics experiment. Apollo astronauts left retroreflectors on the moon's surface, basically high-quality mirrors that bounce light straight back to where it came from. On Earth, you fire a very short, intense laser pulse at the moon, aimed at one of those reflectors. You know when you sent it to a fraction of a nanosecond. You then wait for the tiny trickle of returning photons and record their arrival time, again to a fraction of a nanosecond. The average distance to the moon is about 384,000 kilometers, around 239,000 miles. Round trip, the light path is about 768,000 kilometers. At sea, the flight time is about 2.56 seconds. If you can time the return to better than a nanosecond, you are resolving range changes at the level of tens of centimeters. By repeating and averaging huge numbers of pulses and correcting for atmosphere and instrument effects, you can track the Earth-Moon distance to millimeter scales. That lets scientists see that the moon is slowly drifting away from Earth by a few centimeters per year. It lets them test parts of general relativity, like how gravity affects light travel time. Once again, high-precision clocks plus a fixed C turn the Earth-Moon system into a laboratory tape measure that reaches hundreds of thousands of kilometers with millimeter sensitivity. And it doesn't stop with astronomy or navigation. A lot of everyday and industrial tech is basically send the pulse, wait for the echo, multiply by C. Weather radar sweeps the sky with microwaves and times the returns from raindrops and hail. Air traffic control uses radar to track planes by distance and heading. All based on this many nanoseconds of delay means this many meters of range. On smaller scales, in medical imaging like optical coherence tomography, doctors use near-infrared light and interference to see inside tissues. They send light into your eye or skin, split the beam, and recombine reflections from inside the tissue with a reference path. Tiny differences in travel time, in the range of picoseconds, correspond to micrometers of depth, so they can build cross-sectional images of your retina or arteries without cutting anything open. You're turning femtosecond or picosecond path length differences into three-dimensional maps of living tissue, all by trusting C and building instruments that can resolve absurdly small time shifts. Industrial systems do similar things at different scales. Distance sensors on production lines fire laser pulses and time the returns to measure positions of parts. Autonomous vehicles use combinations of radar and lidar, all based on pulses and echo times, to build real-time maps of their surroundings in meters and centimeters. Even when you don't see speed of light written anywhere, it's there, in the firmware, in the constants compiled into chips, in the tables engineers use when they convert nanoseconds to meters. So the constant that started as an astronomical curiosity is now a silent backbone. GPS navigation, global fiber links, moon ranging, radar, lidar, medical imaging, they all assume C is exactly the value we've defined, and that the universe plays along. And because those systems actually work day after day across billions of users and devices, that's an ongoing, planet-scale confirmation that the speed we measured with moons, mirrors, and math really is a fundamental feature of reality. But there's one more step in how deeply we've committed to that idea. It's not just that C shows up in our equations and technologies. At some point, metrology flips the logic entirely and says, we trust this number so much, we're going to define our basic unit of length. When you say 1 meter now, you are secretly saying this fraction of a light second. That's how far we've gone from does light even have a speed to we define distance by how far light goes in a set time. How far do you have to trust a number before you let it redefine what 1 meter even means? For most of history, a meter was a physical thing. First, it was tied to the size of Earth, then it became an actual metal bar in Paris, sitting in a vault. If you wanted to know how long a meter was, in principle, you went and compared your stick to that bar. Later, people refined this and defined the meter using a specific color of light from Krypton 86, so a certain number of wavelengths of that orange-red light. Better, but still, length was the primary thing, and light was used to describe it. By the late 20th century, that hierarchy flips. After decades of work from people like Fizeau, Foucault, Michelson, and all the modern timing and frequency experiments, the speed of light in vacuum is known to such absurd precision that the uncertainty in C is smaller than the uncertainty in the physical meter standards. There's a mismatch. You're using a fuzzy length standard to measure a sharp speed. Metrologists hate that. So in 1983, the international community does something that sounds small but is actually radical. They stop treating C as something to be measured and instead declare, in vacuum, the speed of light is exactly 299,792,458 meters per second. No error bars. Exact. Once you do that, you can't keep the old definition of the meter, so they redefine it to match the new reality. The meter becomes the distance light travels in vacuum in 1 divided by 299,792,458 of a second. In other words, you define the second first from atomic physics, and then you let C convert that time slice into a length. The old metal bar in Paris is no longer the ultimate reference. It's just a historical artifact. Why base it all on time? Because by then, time is what you can measure best. Atomic clocks, especially those based on cesium-133, can count cycles of a specific microwave transition with fractional uncertainties down at 1 part in 10 to the power 16 or better. That means if you ran the clock for about 300 million years, you'd expect it to drift by less than a second. Length standards made of metal, or even based on fixed wavelengths, simply cannot match that stability because materials expand, contract, age, and respond to temperature and environment. So the strategy becomes define the second from an atomic transition, lock c to an exact number in meters per second, then define the meter as however far light goes in that tiny fraction of a second. Length becomes a derived quantity, built from time and a fixed conversion speed. The thing Roemer only roughly estimated from 22-minute delays in Io's eclipses becomes a pillar of the entire measurement system by definition. Once that choice is made, it propagates everywhere. Calibrating a laser, you're ultimately referencing your wavelength to a frequency, and that frequency is tied back to an atomic standard, and C. Building and aligning an interferometer to detect gravitational waves with arm lengths of kilometers but sensitivity to changes smaller than a proton diameter, your length readout is an interference pattern, which is interpreted using the fixed value of C and the timing of light cycles. Running GPS, your distance estimates from satellites are fundamentally time differences multiplied by C, and the time comes from atomic clocks that are themselves defined in the same system. Go down to industry. A chip factory printing features at tens of nanometers, tens of billionths of a meter, uses lithography machines and interferometers that all trace back, through calibration chains, to the definition of the meter via C and the atomic second. A lab measuring the radius of a hydrogen atom uses spectroscopy and scattering experiments that rely on known frequencies and wavelengths, again underwritten by the same fundamental definitions. A cosmologist quoting the diameter of the observable universe in billions of light years is, in a very literal way, using the same stopwatch you use to define 1 meter on a lab bench. So you've gone from a chunk of metal in a vault to a definition that says distance is what light covers in this much time. That's not just an engineering choice, it's a statement of how seriously we take C. You're saying we trust the constancy of this speed more than we trust any artifact, more than we trust any length carved in metal or etched in glass. You're also saying that time, not distance, is the fundamentally measured thing, and distance is what you compute from it. There is a philosophical punch in that. The story started with people arguing whether light had any travel time at all. Was it infinite? Was it just too fast to see so we could treat it as instant? Then, step by step, you got crude bounds from lanterns, then rough values from Jupiter's moons, then cleaner values from stellar aberration, spinning wheels, rotating mirrors, and finally, electronics and atomic clocks. Each step made the speed more real, less negotiable. By 1983, the confidence is so high that instead of asking, what is C in meters per second, you ask, what is a meter given that C is this exact number? At that point, the constant isn't just in your equations, it's in your language for describing the world. Every time you say meter, hidden inside that word is this fraction of a light second. Every construction drawing, every GPS coordinate, every quoted distance to a planet carries that choice. That's how deep the measurement of C has sunk into the way humans talk about reality. Which sets up the final question. If chasing this one speed led you from philosophical guesses to time-dilated spacecraft, from moons and mirrors to redefined units, what did it really teach you about the universe itself? Not just about light, but about causality, about how fast you can ever go, and about what reality right now even means. How much of what you see is actually now, and how much is just your brain pretending? At the start of this whole story, your senses said light was instant. Flip a torch on, room lights up, no delay, end of discussion. But experiment after experiment smashed that comfort zone. Galileo's lanterns showed that human reflexes are hopelessly slow. Roemer's timing of Io's eclipses showed real, minute-level delays across Earth's orbit. Bradley's aberration showed that Earth's motion and light's speed mix into tiny but precise angles. Fizeau's spinning wheel turned microsecond gaps into on-off flashes. Foucault's rotating mirror converted microseconds into millimeter shifts. Michelson's long baselines pushed all of that into 5 significant figures. Step by step, instantaneous collapsed. You didn't just learn that light has a speed, you learned that the speed is finite. And that one fact forces an ugly conclusion. You never see the universe as it is right now. You only ever see it as it was. The sun in the sky is already 8 minutes old by the time its light hits you. Jupiter is tens of minutes old. The nearest stars are several years old. Distant galaxies are millions or billions of years old. Reality has a built-in delay, and that delay is non-negotiable. It's set by C. Once C is established as finite and fixed, it stops being a detail and starts being the backbone. Maxwell's work on electricity and magnetism doesn't just have a random speed in it. The natural wave speed his equations predict matches the measured speed of light. Special relativity takes that same speed and says, this is the one thing every inertial observer agrees on. General relativity extends the logic to gravity. Even changes in gravity, gravitational waves from violent events like black hole mergers, move at that same speed. Quantum field theory, the framework for particle physics, writes the same constant into the relations between energy, momentum, and mass for relativistic particles. Look at some of the places C shows up in plain language. In mass-energy equivalence, the energy stored in a mass at rest equals that mass multiplied by the square of C. In space-time geometry, the distance between two events in four-dimensional space-time combines C times the time separation and the three spatial separations in a very specific way. In cosmology, when you talk about the size of the observable universe, you're talking about how far light can have traveled since the Big Bang, with C as the speed in that calculation. In gravitational waves, the ripples observed by detectors like LIGO arrive with a speed that, within experimental error, matches C as they cross hundreds of millions of light years. So the same 300,000 kilometers per second that started as the speed of light is now setting the speed at which changes in electric fields, magnetic fields, and gravity itself propagate. This is why modern physics feels so tightly connected. You tweak C, you don't just change optics, you change electromagnetism, relativity, quantum fields, and cosmology all at once. Everything leans on that constant. Then there's the very human part. How this speed sets the scale of your possible journeys. Rockets today push around 11 kilometers per second, roughly 25,000 miles per hour, just to escape Earth. Probes like the Voyagers have reached tens of kilometers per second relative to the Sun. That sounds fast until you compare it to C. 11 kilometers per second is about 1/27,000th of light speed. 30 kilometers per second is about 1/10,000th of light speed. You're not even at 1%. You're at a tiny fraction of 1%. Run the numbers for interstellar travel. Alpha Centauri is about 4.37 light years away. At 10% of light speed, around 30,000 kilometers per second, or about 67 million miles per hour, a one-way trip would still take over 40 years. That ignores acceleration and deceleration time, which would stretch things further if you don't want to smash the crew with extreme G. At 1% of light speed, about 3,000 kilometers per second, the trip time jumps to centuries. So when you seriously treat C as a hard speed limit, you immediately see how vicious interstellar distances are. Measuring C didn't just give you a nice constant for equations, it told you how ambitious you have to be if you want to think about real interstellar journeys, and how brutal the trade-offs are. No matter how clever your propulsion system, as long as you respect relativity, you're negotiating fractions of C and accepting that even fast trips to nearby stars eat big chunks of a human lifetime or more. And yet, we keep checking that limit. We don't just take old lab numbers and call it done. Today's tests of C are spread across scales and energies that Galileo couldn't have imagined. Astrophysicists look at gamma-ray bursts billions of light years away, violent explosions that emit photons across a wide range of energies. If high-energy photons traveled even slightly faster or slower than low-energy ones over those distances, you'd see them arrive spread out in time in a way that doesn't match the emission physics. Observations put very tight bounds on any such difference. Gravitational wave detectors catch ripples from merging black holes and neutron stars. In some cases, you see both gravitational waves and light or other electromagnetic signals from the same event. If gravity waves traveled at a different speed than light, they would arrive noticeably earlier or later relative to the photons. So far, they line up within very small margins. That's a direct cosmic scale check that speed of gravity and speed of light are the same constant. On Earth, precision cavity experiments bounce microwaves or optical waves back and forth between mirrors in resonant cavities, looking for tiny changes in frequency that would signal any directional dependence of C, any slight variation as Earth rotates or orbits the Sun. These experiments are like modern supercharged Michelson-Morley tests. To the sensitivity we can reach, C stays direction independent. All of these are different ways of asking the same question. Does C ever flinch? Does it depend on energy, on direction, on time as the universe expands, on gravitational potential? So far, every serious test says no within incredibly small errors. That doesn't mean it will never fail. Science never fully closes that door, but it does mean that for now, the constant you dragged out of lanterns, moons, stars, wheels, mirrors, lasers, and atomic clocks looks unshakable. So what did measuring the speed of light really teach you about reality? First, that your senses are not a final authority. They said instant, the universe said finite. Second, that one number can end up threading through everything, from how your phone knows where it is, to how stars shine, to how black holes collide. Third, that there is a hard speed limit for any influence, and that limit is what forces time and space to behave the way they do. You started with a simple question: does light even have a speed? You ended with a constant that defines your units, fixes your cosmic horizon, caps your maximum travel speed, and decides which events can ever affect which others. And after centuries of trying to break that constant, every test so far still points to the same conclusion. This speed is not just large, it's fundamental. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.